See, those who are online are able to hear me. Am I audible?
Yes, sir.
Okay. Just a minute, guys. We'll get started. Shall we get started?
Yes, sir.
Yes, sir.
You guys can move front. Hey, Sanjay, Vishal, and Adav, you can move front. And come here. See, those who are online are able to see the screen?
Yes, sir.
Perfect. Right. Ready? Okay. So we have started with magnetism in the 4th chapter, right? We understood that moving charges will generate magnetism, right? And we understood how magnetism is generated in permanent magnets also. Now the next question is, if moving charges are able to produce magnetism, is the reverse possible? In the sense, with the help of magnetism, is there a possibility for you to generate electricity? So that's what is dealt in this chapter called as electromagnetic induction. So that is what we are going to deal in the chapter electromagnetic induction. As the name suggests, right, if you're going to break it into 3 parts, electro refers to charges. Magnetic refers to magnetism. And induction refers to no physical contact. So it refers to no physical contact. So if there is a possibility where you can generate electricity using magnetism without any physical contact, then you call that branch as electromagnetic induction. And that is what we are going to deal throughout this chapter. Am I clear with this point? Right? Okay. So what is going to happen? Current is generated. So current is generated using magnetism without any physical contact. Without any physical contact, right? And that's what is called as electromagnetic induction, or in simple terms, you call it as EMI. We call it as EMI. Is that clear? Right. Now, we need to understand how this is happening in the first place, right? Now, we have a small simulation table here, right? Now observe. In the 4th chapter, what we discussed is about an electromagnet. In the sense, you have a battery that is connected to a wire, right? If you're going to pass current through it, you can observe magnetic field getting generated. Means the compass will respond to the field, right? You will be able to see the direction. This is what is an electromagnet. I hope you remember. So what is an electromagnet? So with the help of electricity, you're going to generate magnetism, and it is also going to be a temporary magnet. Why is it temporary magnet? It will exhibit magnetism as long as the current is flowing through it, right? Now, what we are going to have is, we are going to have exactly the reverse of it. In the sense, we have a coil. The coil is connected to a bulb, right? It is like a sensor to detect whether current is flowing or not. So when it is connected to this bulb, we are going to use magnetism to generate electricity in this, right? For which, if you observe, if I place this coil here, okay, if I place this coil here, now I have this magnet in my hand, right? Observe what is going to happen when I'm going to move that magnet. When I'm going to move that magnet, see what is going to happen. Did you observe? So, when you move the magnet, when I was moving it closer, you could see that there is some glow in the bulb. When I move it away also, there is some glow in the bulb. In both the scenarios, there is a slight glow that is taking place in the bulb. Question is, why is it even happening? Right, that is what we will try to answer in this chapter. That is the first point we will answer. Based on that, we will see what are all the laws that are constructed on top of this observation. Okay, the first important observation, what does it state? If you have a coil, you should not have an open conductor. What is that you need to have? You need to have a coil, means it should be a closed surface. If there is a coil across which you try to change the magnetic field. Okay, I'll come to that point. More precise, it is not the magnetic field, you're changing the magnetic flux. So when you move this, right, when you move this magnet, what is happening? You're able to see the number of field lines that are associated with this coil. So when I move the pole closer to this coil, is the magnetic flux going to increase or decrease? Why will it increase? Because magnetic field is more strong closer to the pole. When the pole itself is moving closer to the coil, then the magnetic flux is supposed to increase. Similarly, when you move the pole away, did you observe in both the scenarios, when I moved the north pole closer and the north pole away, in both the scenarios, there was this bulb glowing. So what happened? When you move the north pole closer, you increase the magnetic flux. When you move the north pole away, you decrease the magnetic flux, where in both the scenarios, you could see that the current was getting generated till the time I was moving it. As soon as I stopped moving this magnet, you could have seen that the current will also get cut off. Did that happen? So the most important point here is, it states, if there is a change in magnetic flux associated with the coil. What is happening? If there is a change in magnetic flux associated with the coil, electric current can get generated. So what does it say? If there is a change in magnetic flux associated with the coil, electric current will get generated. Makes sense? So that's what you're able to observe, no? And this law is what is called as Faraday's law of electromagnetic induction. This is what is called as Faraday's law of electromagnetic induction. Am I clear with this point? Right. Okay. So first, I'm going to start with this statement. So what does it state? It states, if there is a change in magnetic flux. What is magnetic flux? It is represented by the same symbol phi, like how electric flux is represented, but the subscript used here is going to be capital V. So if you write phi with subscript E, you call it as electric flux. If it is V, you call it as magnetic flux. So if there is a change in magnetic flux within a coil, right? So, but most important point is, you should have observed that coil should not be connected to any battery. If it is connected to battery and current is flowing, then it is cheating. Then there is no question of electromagnetic induction, right? It should not be connected to any coil. That is why, since this coil is picking up the magnetic flux, this is also given a name called as pick-up coil, because this is picking up the magnetic flux, right? So if there is a change in magnetic flux within a coil, to be more specific, a pickup coil, with respect to time. So with respect to time, what is that you can observe? You can observe that electric current is induced in the coil. You can observe that the electric current is induced in the coil. Am I clear with this? All right. And mathematically, if you observe, this states that EMF that is getting generated. Because if you want the current to flow, right, what is most important? Potential difference. That potential difference is given a name called as EMF. So Faraday's law of electromagnetic induction can be mathematically stated like this: that EMF generated across a coil is observed to be directly proportional to the rate of change of flux. So it is directly proportional to the rate of change of what flux? Magnetic flux. Because there will be a question asking, stating that, can change in electric flux generate EMF? Listen to my question carefully. If they put a question stating that, can change in electric flux generate EMF across the coil? The answer is no. Only the change in magnetic flux with respect to time can generate EMF. So EMF is directly proportional to delta phi b divided by delta t. So from here, you can observe that EMF is equal to minus delta phi b divided by delta t, and this minus sign is the significance of a law called as, so it is a significance of a law called as Lenz's law. Okay, it is a significance of a law called as Lenz's law. So EMF is equal to minus delta phi b divided by delta t, and this will be the average value. If suppose you want to find the instantaneous value, then EMF can be directly stated as EMF is directly proportional to d phi b divided by dt. So it is directly proportional to d phi b divided by dt, which implies EMF is equal to minus d phi b divided by dt, where this will be called as the instantaneous value. This would be called as the instantaneous value. Okay. So I hope it is clear. Right. Now, we understood that for EMF to get generated, there should be a change in magnetic flux associated with the coil, and that should change with respect to time. Am I right? Now the question is, what is magnetic flux in the first place? So magnetic flux, if I represent it with the symbol phi b, what is going to be the magnetic flux? It is going to take the similar definition as that of electric flux. What do we state as the electric flux as? It is the number of magnetic field lines. It is the number of magnetic field lines that pass through a surface perpendicular to it. That's it. So if I take this to be the coil, right? If I take this to be the coil, where the coil is in this orientation, right? If I take the field lines to be in this way, where I'll call this as B. Now, if I take a point here, and for this point, for this coil, if I define the aerial vector, we know that the aerial vector is going to be perpendicular to the coil. So then the angle between B and A, I'm taking it as theta. So how is the magnetic flux defined as? There is a number of magnetic field lines that pass through a surface perpendicular to it. So I need to take the component of B perpendicular to it. So what is the component of B that is perpendicular to it? It is B cos theta. So the magnetic flux is mathematically defined as B cos theta multiplied with A. So it is going to be B A cos theta, or this is also equal to B vector dot A vector. Right? So what is it going to be? Is it going to be a scalar or a vector quantity? It's going to be a scalar quantity because it's a dot product between two vectors. Right? So what is going to be the SI unit for it? So what is going to be the SI unit for it? So Tesla meter square, and this is what is called as Weber, WEBER, which is represented by the symbol capital W and a small b. Okay. Is the point clear? B is here, theta is here. The vector closer to theta is cos. No? I told perpendicular to the surface. I didn't say perpendicular to the aerial vector. Clear, Ada? Right. Now what we'll do is we'll try out a few problems that are based on magnetic flux and Faraday's law of electromagnetic induction. Okay. Can someone give me your textbook? So let us look at example 6.2 in your textbook. So example 6.2 states a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. It's placed vertically in the east-west plane. A uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. Okay. The magnetic flux is decreased to 0 in 0.7 seconds at a steady rate. Determine the magnitude of the induced EMF and the current during this interval. So let's collect the data. It says there is a square loop of side 10 centimeter. So this can be written as 10 into 10 power minus 2 meter or 10 power minus 1 meter. Right. And resistance of this coil is given as 0.5 ohm. 0.5 ohm. And it is placed vertically in the east-west plane. Okay, it is placed vertically in the east-west plane. And there is a uniform magnetic field of 0.1 Tesla that is initially present, right? And there is it is present at an angle of theta is equal to 45 degrees because it is generated in the direction of northeast. So northeast means what is the angle that you are going to take into consideration? It will be 45 degrees, right? So it is in the direction of northeast. The magnetic field is decreased to 0 in 0.7 seconds. So B initial is 0.1 Tesla, B final is going to be 0 Tesla. So it is decreased from 0.1 to 0 in how much time? In time of 0.7 seconds. So our job is to find the magnitude of the induced EMF and the current in this coil. So if you observe, what is going to be the EMF? So EMF is equal to negative of delta phi B divided by delta T. Here I took delta because the time is not instantaneous, it is a specific value. They didn't ask instantaneous. Had they asked instantaneous, I would have taken d phi by dt. Right. But since we want only the magnitude, I'll take modulus of this. So this will be delta phi B divided by delta T itself. But what is delta phi B? It is the final flux minus the initial flux, the whole divided by the time that has been taken. That is delta T itself. So what is the final flux? Magnetic field. So final magnetic field into area. Area of the coil did not change. Final, see, the flux is changing due to whom? Remember this. Flux is equal to what is the formula I gave you? It is BA cos theta. So if you want flux to change, right? So throughout this chapter, we'll be concentrating only on flux. So if you want the flux to change, one parameter will be changed and the other two will be kept constant. So you can ask me what are the three parameters? One is B, one is A, and the third is theta. In this problem, if you see, the flux is changing due to whom? Is it because of the area of the coil, theta, or magnetic field? It is because of the magnetic field. This is what is decreasing. Theta is kept constant, area is kept constant. Makes sense? So that is why I wrote B final into, I didn't write it as A final because area is the same. Similarly, I'll write it as cos theta minus, what should I write? B initial A into cos theta, the whole divided by delta T. So what can I take out? So B final is how much? 0 minus B initial is how much? 0.1 into what is the area? Area, see, side is 10 power minus 1. Since it's a square, area is going to be a square. It will be 10 power minus 2 into cos of, how much should the angle I need to take as? 45. So cos 45, the whole divided by 0.7. Makes sense? Right? So, but still remember, I need to take only the positive value because they asked only the magnitude. So 0.1 into 10 power minus 2 is 10 power minus 3. So it will be 10 power minus 3 into, observe this, cos 45 is 1 by root 2, no? Cos 45 is 1 by root 2. You can take it as root 2 divided by 2. Root 2 is 1.4 divided by 2, it will be 0.7. So actually it is 1.414, you will get it as 0.707. So since in this problem it is 0.7, I'll cancel this 0.7 and cos 45. Because cos 45 is 1 by root 2, same as 0.7. So what is it you're left out with? 10 power minus 3 into, you're left out with 1. Answer will be 10 power minus 3 volt. So the EMF that has got generated is 10 power minus 3 volt. Is that point clear? Am I clear with this? This is the magnitude of the EMF that has got generated, but they are asking the magnitude of the induced current also. So if I want the magnitude of induced current, I is equal to E divided by R. So what is the value of R? It is 0.5. So 1 divided by 0.5 is how much? 1 divided by 0.5 is 2. See, E is 10 power minus 3. So can I write it as 1 into 10 power minus 3? So I'm taking 1 divided by R. R is 0.5. 0.5 is 2. So 2 into 10 power minus 3 will be the answer. But 2 into 10 power minus 3, I should write it in terms of ampere. So to put it simple, the EMF is going to be 1 millivolt and the current is going to be 2 milliampere. Is that clear? Done with this? So I'll give you 2 minutes time. Try out 6.3. Try out 6.3. Here's the question. You can copy it. So circular coil of radius 10 centimeter, 500 turns and resistance of 2 ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter through 180 degrees in 0.25 seconds. Estimate the magnitudes of the EMF and the current induced in the coil. Horizontal component of the Earth's magnetic field is 3 into 10 power minus 5 Tesla at that place. Anybody with the answer? Those are online. Those are online. Anybody with the answer? You solved it or not? Phi is the initial flux, huh? Both are same. Okay. Then subtract both. What is EMF? EMF is the difference in flux divided by time, no? So listen. So this question says a circular coil of radius, right? Radius is 10 centimeter, which is going to be 10 into 10 power minus 2 meter or 10 power minus 1 meter. So a coil of coil of radius 10 centimeter has 500 turns. Capital N is equal to 500 and resistance of how much value? Resistance of 2 ohm is placed in a plane perpendicular to the horizontal component of the Earth's magnetic field. So, if this is the direction of Earth's magnetic field, the coil is placed perpendicular to it. Okay, so the coil is placed perpendicular in the sense, what will be the initial angle between the magnetic field and the aerial vector? listen to this carefully. Okay, one common mistake that happens is when we read this, coil is placed perpendicular to the magnetic field. Most of them take the value of theta to be 90 degrees. Don't do that mistake, because angle is not measured between the magnetic field and the plane of the coil. Angle is measured between the magnetic field and the area of the coil. So if the magnetic field and plane are perpendicular, magnetic field and areal vector are parallel. Make sense? Right. So is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about its vertical diameter through an angle of 180 degree in 0.25 seconds. So initially, if the coil was like this, then the areal vector would have been like this. So this is the direction of field. Field is not changed. But what is happening now? The coil is rotated through 180 degrees. So what is going to happen between the magnetic field and the areal vector? Theta is going to be 180 degrees. Are you able to visualize it? Right? So what is the value of magnetic field that is going to be in both the cases? It is 3 into 10 power minus 5 Tesla. It is rotated about its vertical diameter through an angle of 180 degrees. In the time of delta t is going to be 0.25 seconds or 1/4 of a second. Right? So estimate the magnitudes of the EMF and the current induced in the coil. So it's simple, no? So what is the formula for EMF? EMF is equal to delta phi B divided by delta T. So what is going to be the value of delta phi B? B into A into cos theta final. Did you observe how I wrote it? Because theta is the one which is changing here. Minus B into A into cos theta initial, the whole divided by, how much is it going to be? It is going to be delta T, right? So this will be equal to, what is the value of B? 3 into 10 power minus 5 Tesla into, what is the value of A? Area is going to be pi r square. So pi into 10 power minus 2. So pi into 10 power minus 2. So if you observe here and here, dA is common. So I have taken it out. So what should I write inside? Cos theta final is how much? Theta final is 180. So cos 180 is minus 1. Minus is in the equation. What is cos theta initial? Theta initial is 0. Cos 0 is 1. So minus 1 is going to be minus 2 divided by the time taken is going to be 1/4. Am I clear with this point? Right. So now what will happen is 3 pi into this is going to be minus 2. So I'm going to take modulus because they asked only the magnitudes. So is it not going to be 24? See, 4 will go to the numerator. 4 into 2 is 8. 8 into 3 is 24. So 24 pi into 10 power minus 7 volt. Right? This is supposed to be the amount of EMF that is getting generated. Right? So what is the answer given? 3.8 into 10 power minus 3 r. Into? We forgot that, yeah. I didn't take the number of turns. So I'll rub this part alone. Okay. So for this, what is the value we are going to get? We will get 24 pi into 10 power minus 7. But that is going to be the EMF that is generated by one turn. But how many turns do we have? We have 500 turns. So we are supposed to do into 500. So how much is the answer going to be? 5 into 24 is going to be 120. So 120 pi into 10 power. So 10 power minus 7 into 10 power 2 is going to be 10 power minus 5. It is going to be 10 power minus 5. So what you can write this as? You can write it as 1.2 pi into 10 power minus 3 volt. So 1.2 pi into 10 power minus 3 volt will be the answer for EMF. What about the current? So I will be equal to E divided by R. So E is going to be 1.2 pi into 10 power minus 3. What is value of R? R is 2. So you will get the answer as 0.6 pi into 10 power minus 3 ampere. So 0.6 pi into 10 power minus 3 ampere. That will be the answer. Is that clear? Yeah. So make a note of. Am I clear? Shall we proceed? Okay. So the next important concept that we need to understand is this thing, right? Okay. This is something we are going to discuss now. Right. See, the next topic that we are supposed to discuss is called as Lenz's law. So here, what I'm going to do is, for Faraday's law of electromagnetic induction, we understood that if there is a change in magnetic flux taking place with respect to time, EMF is induced. So I told you when I wrote the mathematical expression, E is equal to minus delta phi b divided by delta t. What is the significance of the minus sign? It is the significance of Lenz's law. What do I mean by that? See, for that, if you observe, right, let's say that this magnet is here. Now, I want you all to observe clearly and tell me what is happening when I move the north pole closer to this coil. I want you to concentrate on the direction of electrons. Okay. See what is happening when I move the north pole closer to this coil and when I move the north pole away from that coil. Okay. So observe this. What happened? They moved in the downward direction. Did it move in the upward direction? See, I'll do it again. I'll bring it faster. See. Downward. Did it move in the opposite direction? Now what I'll do is, okay. So that is something that happened when I moved the north pole closer. Now observe what is, so did you remember when I moved the north pole closer, the electrons moved downward. When the north pole was moved away, it moved upward. When I move the south pole, see what is going to happen? Downward. When I move the south pole away, it is moving upward. So shall we try it again and see? Downward and it is upward. So it is going in the opposite direction. So what do I mean by this is, right? So what do I mean by this point is, listen to this carefully. You're observing this coil, right? So when you see from this side, these these blue color dots are electrons. So when you see from this side, when the south pole was moved closer, you would observe that the dots were moving in the downward direction. So what is the direction of current? So direction of current is upward. In the sense, when the south pole was moved closer, the current started moving in the clockwise direction. Whereas when the south pole moved away, the current was flowing in the anti-clockwise direction. Now go to the concept of the current carrying loop as a magnetic dipole and tell me, if the current is flowing in the clockwise direction, what kind of a pole is going to get generated? It will be south pole. Meaning, if I took the south pole closer, what happened? Electrons moved downwards. So current moved in the clockwise direction. So it started behaving like south pole. Whereas when I moved the south pole away, the electrons were moving upwards. Current was moving in the anti-clockwise direction. It started behaving like a north pole. The same thing happened when the coil was this side and the north pole was this side. So when you move the north pole closer, what happened? When you move the north pole closer, see, observe. When you move the north pole closer, right, electrons move downward, but you're seeing from this side. When electrons move downward, current is moving upward. So it is going in the anti-clockwise direction. So anti-clockwise means it is behaving like north pole. So when the north pole was moving closer to this coil, it generated north pole. When the north pole was moving away from the coil, it generated south pole. So did you understand one thing? Did you understand this concept? So the observation that we need to take from this is, when you try to increase the flux, that is, when you move the north pole closer to the coil, what pole got generated? North pole itself got generated. So when you try to increase the flux, the same pole got generated. When you try to decrease the flux, opposite pole got generated. So the same thing was happening with south also. Does that make sense? Right. So what is the important observation to be taken from here is, the important observation to be taken from here is something like this. Observe. Right. When you moved the north pole, the current was flowing anti-clockwise and the north pole itself got generated. When you moved the north pole away, the opposite pole was getting generated and you had the south pole taking place. Is it clear? So what is the statement here is, Lenz's law states that magnetic pole induced in the pickup coil will be in such a way that it will always oppose the cause. Magnetic field, sorry, the pole induced in the pickup coil will be in such a way that it will always oppose the cause. In the sense, if you try to increase the flux, listen to this first. If you try to increase the flux, irrespective of whether you are moving north pole or south pole, if you try to increase the flux, the same pole will get generated so that north and north will repel. So you are trying to increase the flux. No, the pole is getting generated in such a way that it is trying to decrease the flux. Means saying it is good, you go away. Means this pole is telling, the pole that has got generated here is telling that you go away. So when you try to increase the flux, it says, I will decrease it. When you try to decrease the flux, what is happening here? Opposite pole is getting generated. Means it is trying to increase the flux by pulling the north pole closer. So exactly the opposite will happen. That is the meaning of opposing the cause. Who's opposing the cause? The induced magnetic poles are opposing the cause. So just to put it simple, if a pole is moved closer, same pole is generated. If a pole is moved away, opposite pole is generated. That's it. Okay. Am I clear with this? Right. And another important point to be noted here is, Lenz's law is based on the concept of conservation of energy. So it is based on the concept of conservation of energy. Materials, right? So we can try out one or two problems. Problem in the sense there are no numerical or that you have to update and find the direction of. Okay. Shall we try that? Do the wrong and I will understand. One problem. Yes. Example 6.4, it states figure 6.7 shows planar units of different shapes moving out of or into a region of magnetic field, which is directed normal to the plane of the loop, away from the leader. In the sense, the magnetic field is away, but what is happening? There are three different loops which are trying to move either in or out of the plane. Okay, out of the magnetic field. Determine the direction of induced current in each loop in the length. So determine the direction of induced current in each loop using Lenz's law. So how are we supposed to solve? If you observe, when this coil is moving into the plane, what is happening is the flux increasing or decreasing. See, logic is very simple. Flux increases, okay, flux increases, then there will be same pole. Flux decreases, then it will be opposite pole. I hope it is clear. That is all Lenz's law has to state. So here what is happening? The flux is increasing. So flux increasing means it should be same pole, right? Listen to this carefully. Since the magnetic field is into the plane, this board, if I take it as a plane, this is the plane, this is receiving the magnetic field lines. So if I stand here facing the board, I am emitting the field lines, the plane is receiving the field lines. So I am acting like North Pole and the board is acting like South Pole. Now, if you observe, this coil that is moving into the magnetic field is actually facing me. So what am I? I am the North Pole, right? So flux is increasing means the current in this should get generated in such a way, it depends on what I am. Since I am the North Pole, the current will be in the anti-clockwise direction. So flux increases, same pole as that of me. So I am North Pole, so there will be the current in this in the anti-clockwise direction. So anti-clockwise means what will you write? You can write A, B, C, D. If you write it as A, B, C, D and leave, you're wrong. You should always write it as A, B, C, D, E. So whatever you started with, you should end with the same. Only then it will become a loop. Did you understand this? Right? So this is the answer for the first question. Second one is, now you can answer the other two in 2 seconds. It's very simple. What is it? This one is moving out of the plane, out of the magnetic field. So here the flux is going to decrease. So flux is decreasing means opposite pole. So opposite pole as that of whom? As that of us. Yes, north pole. So it should be clockwise current. So clockwise means it should be ACBA. So current will be in the direction of ACBA. What about this? The coil is moving away. So again flux is. So can you tell me why the flux is decreasing in the first place? Because the area is decreasing. So orientation is same, magnetic field is same, but area is decreasing. So flux decreasing means opposite pole. So opposite pole means opposite. So I am north pole. So it should be south pole. Current will be clockwise. No? So it will be AB, CD. That's it. Am I clear with this? That's it. So this is how you are supposed to solve problems based on Lenz's law. Is that clear? Right? So these are the two important basics of this chapter. We have actually completed the important part. Remaining is only derivation. And this chapter, unlike the previous one, has a little bit of mathematics. Okay, but I'll take care of it, don't worry. So let's see. Clear with this? Right. So tomorrow's class will start with few more problems based on Lenz's law. That is, in the exercise also, we have problems based on Lenz's law, the first two problems. We will solve them, and then we'll go to the subsequent part of this chapter. Clear? So just make a quick note of it. Then we... Those are online, am I clear?
Yes.
Okay.
Sir.
Yeah. So if there are no questions, we can wind up.
Thank you, sir.
Yeah.
Thank you, sir.
You asked me a problem, Kada. కొంచెం టైం అవుతుంది సో లేదా వేరే డౌట్